Okay, so welcome back to the fourth lecture in Matt Novack's lecture series on anomalous dissipation and the strong Onsager conjecture.
Thank you. All right. Thanks again for coming back. So the goal today is to talk about this idea of replacing an Fourier series with wavelength series. All right, so let's start with our iterative setup again. So we have the Euler-Reynolds will come as usual. And I'm not setting it up wavelet style because I want to set it up as we've been setting it up so far so that we can see why we're forced to change the point of view. So then we add in the last one letter inequality. Over here we add same as before. Right, so we call this Euler-Reynolds, and this was Maxwell's average inequality. And we have our equal parameters. So lambda q frequency, delta q was amplitude, beta was the regularity. And we added this intermittency parameter at the end of yesterday, which we call RQ. And it was lambda q over lambda q plus 1 over 1. All right. And then when we set up the L3 iteration, we had inductive estimates, which said that radius in space of RQ should be measured in L3 halves. And they were bounded by delta plus 1. And similarly, when we take the phi q, the error in the local energy inequality. The important thing that we saw yesterday was that instead of just delta q plus 1 with 3 halves, we picked up an RQ inverse. And that was what saved the day on these errors that were only commensurate with 1/4 regularity in the Holder setting, was this extra RQ in the current error. And we also could take derivatives of the velocity field, and these were measured in L3. And instead of just delta q for 1/2, we also picked up this RQ minus 1/3, which came from the fact that an L3 estimate might pay a little bit of intermittency loss if I've normalized my functions in L2. All right, and then we defined WQ plus 1 equals WQ plus 1 R plus WQ plus 1 phi. And this is now the projection onto all the frequencies in between lambda q plus 1 times RQ and lambda q plus 1 of whatever limiting solution you were building. All right, so we smeared out the frequencies in the velocity. And WQ plus 1R was basically, morally speaking, the square root of the Reynolds stress minus the Reynolds stress, and then we had this high frequency intermittent shear flow, and the LP estimates on this thing were R cubed in 2 over P minus 1 in LP. So if P equals 2, this is normalized in L2, and that was because the nonlinearity here is quadratic. And then we had the WQ plus 1 phi, which was pretty similar, except that we replaced the L2 normalized object with an L3 normalized object. And then the estimates here were R cubed 2 over 3 minus 2 over 3. And this gave us an estimate on WQ plus 1 in L3. And it's exactly the same estimate that you would expect inductively to match the U estimate. So WQ plus 1 over 1/2, R cubed over minus 1/3, lambda Q plus 1. All right, and oh wow, sorry, yes. So, all right, and what we saw at the end yesterday was the Goldilocks rule for RQ, and I've already built it into this choice, but let's just formalize it at a slightly more abstract level. So the basic principle is you take an error at frequency lambda, and what you do is you correct it using a velocity with frequencies in so lambda q plus 1 times RQ is like lambda q to the 1/2 times lambda q plus 1 to the 1/2. So that's lambda to the 1 plus b over 2. It's the average of the frequency of the error and the maximum frequency of the velocity. All right. All right, so this is where we left off. And now we have to see what the cost is for smearing out these frequencies. And I sort of alluded to it yesterday, but let's do it carefully. So let's consider the relaxed local energy inequality, the nonlinear error term, the oscillation error. It comes from W2 plus 1 phi interacting with itself. All right, so this was divergence in phi q plus 1/2. Again, let's just keep the phi piece in here. And the whole point of the definition that we set of WQ plus 1 phi was that at low frequencies, so projection on the frequencies of lambda q of this term was equal to -5. And what's left over after you let the divergence fall and you use these script W for stationary solutions, what's left was something like gradient of phi q, projection off of the mean of the W, the script W. All right, so I'm going to forget that this is a vector field and that there's components. Let's just think of this as a scalar function. All right, and so we want to put this in divergence form, which means we want to estimate divergence inverse of this thing in L1. All right. So we have to think about what are the active frequencies inside the projection off the mean of this script W. And the active frequencies, well, there's no mean. And then everything else is lambda q plus 1 r cubed to lambda q plus 1. That's what's left when I get rid of it. So what I can really, well, let's write it on the line. This is like projection on frequencies in between lambda q plus 1 r cubed, which I guess I'll just write out. Of this W. And I expect the errors at different portions of this frequency spectrum to have different sizes. I know that they're going to have different derivative costs. They're going to have derivative costs depending on the frequency. So let's split this up into a sum. So I'm going to introduce a parameter n bar. And it's basically a large integer that I use to divide the frequencies that I see in this frequency. So the picture is, here's lambda q, here's lambda q plus 1. I'm going to divide this into n bar many pieces. All right, and I'm going to estimate each of those pieces of this frequency projector separately. So I'm starting at n bar over 2 because I'm only starting halfway in between lambda q and lambda q plus 1. And I'm going up to n bar because that gets me all the way to the end. All right, so div inverse gradient phi q. Let's call this p lambda q comma k. So let's say here's lambda q comma 1. Maybe this here is lambda q n bar over 2. And when I get to the end, that's equal to lambda q n bar, which is the same as lambda q. I'm just coming up with a nice shorthand, which refers to which shell in here I'm treating. All right. Now, if you just if you use the div inverse, is basically now going to gain lambda qk in each of these separate terms. And let's imagine that we're taking a very fine frequency chopping so that derivatives also cost lambda qk inside one of these shells. In reality, when I'm in the little one of these shells, the divergence inverse is going to gain the left endpoint and the derivative is going to cost the right end. But let's just imagine that we've taken very fine discretization so that that difference doesn't matter. And you do the computation you get that phi qk. So let's say phi qk is this kth term in this sum. It obeys exactly the estimate you expect. All right, so what do you expect? What you expect is that in general, a phi at frequency lambda in L1, and then when I take some derivatives, so the gradient of a phi at some frequency lambda in L1 is less than delta lambda with 3/2, where this is lambda to the minus 3 beta b. That's consistent with this estimate here, which is lambda q to the minus 3 beta b. So I'm just generalizing this to arbitrary lambda. It picks up the R lambda inverse, and it pays lambda to be n for n derivatives. And R lambda inverse is lambda to the b minus 1 over 2. All right, so this is the exact analog of delta q plus 1 to the 3/2 RQ inverse lambda q. All right. All right, so the point here is that the size of these errors scales perfectly. Size scales perfectly with frequency, meaning if I'm halfway in between lambda q and lambda q plus 1, I get an error which is halfway in between this evaluated at q and this evaluated at q plus 1. All right, so the size scales perfectly, but the frequencies have been distributed rather broadly. But
you are already using the fact that you are in a shell. The fact that you are using lower and upper part. It's not like the finest possible.
we're imagining that this shopping is fine enough that I can ignore the difference between the left and right endpoint of one of these little shells. Just imagine this set of frequencies as a discrete set of frequencies, and divergence inverse gains exactly as much as the derivative costs. This is an epsilon size error that I can.
Then where RQ minus 1 comes from? I mean, W3.
It comes from the same place that this came from. These errors always have an R inverse in them. And so what I'm saying is if you find an error which is at some frequency lambda, it has the exact analog of this estimate, just evaluated at frequency lambda. Right. Maybe I should pause.
No, I
questions.
yeah. A little bit confused, but
Yeah, I mean, if I take you're just interpolating estimates that you would expect here and here to get an estimate in the middle, which is just the average.
yeah,
average of these two
I
estimates.
even don't understand the starting point in the sense that if you think about phi q, it should be L3. In L1, it shouldn't have any RQ minus 1.
No. This was the point of the L3 iteration, is that the L1 estimate on the phi q's, it gained an R inverse. That's how we salvaged this 1/4, this apparent 1/4 barrier and made it a 1/3. Is that we gained this extra R. Okay. All right.
Okay. Yeah.
All right, so let's just draw a schematic, which is describing what's happening. All right. So let's draw the C alpha schematic so that we have something to compare. So let's draw some frequencies. Lambda Q plus 1, lambda Q plus 2. And I'm going to draw two parallel sets of number lines from frequencies. And this one is for velocities. So let's give it a different color. This one is for velocities. And this one is for velocities. All right, so how did the C alpha scheme work? C alpha scheme work. Well, you had some velocity, WQ, at frequency lambda Q, and it created errors. RQ at frequency lambda Q. And you, let's make this a purple arrow because we're making an error term. So we're going to end up with purple arrow. And then we make a new velocity increment, WQ plus 1, which helps us get rid of the error RQ, but it makes some new errors, RQ plus 1. And so we make another velocity. WQ plus 2, and that makes some errors, RQ plus 2. What's happening in the B alpha pre-infinity scheme if I use Goldilocks, which I not so wisely erased? And so we're going to draw the same type of picture where we have velocities, stresses, and we start with the velocity. Let's start down here with an error, RQ. What happens when we make the velocity increment to correct this thing? Well, if here's lambda Q and here's lambda Q plus 1, the frequencies are going to live not just at lambda Q plus 1, but in between lambda Q plus 1 RQ and lambda Q plus 1. So the picture is like this. So you make a velocity WQ plus 1, which has frequencies everywhere in between the midpoint between lambda Q and lambda Q plus 1 and lambda Q. And we then diced up these errors into separate little shells, and they make a whole spectrum of new stress errors all down here. And now what's the problem? Well, let's use the Goldilocks rule again because it seems to be the thing that works. Right? We make some kind of velocity increment using the Goldilocks rule whose purpose is to get rid of the bottom shell. And when I do that, I fill up half of the shell in between lambda q plus 1 and lambda q plus 2. And if I apply the same procedure to this endpoint, I make another velocity increment to correct this error term. And if I turn all these things into stresses, I have to dice them up into little shells. And what I end up with is stresses everywhere. Or errors. What errors? I guess I should have called this phi q in order to be consistent with the. So we can call this phi q plus 1. 2, so these are just generic errors. And save that. All right, so let me pause and see if there's questions about this schematic. Okay. Now, what I claim is that this smearing out of frequencies is not so good for the linear error terms.
Is that lambda q plus 2 down there?
Yes, sorry. Recall. Okay, now it's right. It's right. Smeared frequencies are bad for the Nash error. So we spent all this work trying to fix one of these Nash errors which occurred in the relaxed local energy inequality, and we smeared out the frequencies and we fixed it. But now I'm claiming that we're back off the river. And why is that? So let's look at the order right off the Nash. So this was the divergence of WQ plus 1 tensor UQ. But let's just call this U old, where by old, I mean frequencies less than lambda Q plus 1. And the reason I'm not putting the subscript Q on it is because I'm going to have velocities that have frequencies all through this range. Okay? So this isn't really a UQ. It's a U everything up to but not including lambda Q plus 1. All right. Now, let's split up the analysis of this thing into different pieces. So the first piece is frequencies less than or equal to lambda Q. That's an analogy with how everything used to work when I had nice discrete frequencies. All right. So here what we really have is WQ plus 1 dot nabla. I'm going to call this UQ. It's a proper UQ. It has maximum frequency lambda Q. And I apply divergence inverse. And I estimate in L3 halves. And what can I hope to find? Well, the divergence inverse will spit out the lambda Q plus 1 inverse in this error term. The WQ plus 1 will cost delta Q plus 1 to the 1 half. r cubed to the minus 1/3. And the WQ actually has frequencies only up to lambda cubed. So I can put delta q to the 1/2 r cubed minus 1 or minus 1/3 lambda. We expect this to be the good term because it only has frequencies up to lambda cubed. And if you write out the arithmetic, you get that this actually is a good term. You get the delta that you want, and this delta is consistent with 1/3 minus regularity. These are the good frequencies. These are the ones that work exactly like the scheme always used to work. All right, but what about the bad ones? What's happening with those? Let's do case 2 of the bad ones, which is frequencies less than the midpoint. All right, so what we're looking at here is divergence inverse of WQ plus 1 dot nabla U. I don't really know what to call this. Let's call this Q comma 1/2, meaning that its maximum frequency is that number right there. All right, we have to estimate this in L3 And if you do the arithmetic, I'm not going to bother doing it on the board, but you get that it's too big. I guess I should not include all the stuff up to lambda cube. So just the frequencies in between the good case and halfway up to lambda cube plus 1. You just write out the estimate using the same principles that we've been using. You just get that it's too big. And the next case is even worse. So let's call this, nabla UQ, I don't know what to call it, 1 minus. So I don't know what the good name is, but the problem with this thing is that it actually has frequency overlap with WQ plus 1. Right? Because WQ plus 1 was supposed to have exactly these frequencies in it. And so I've totally messed up the idea of Nash iteration here, which is, I have high frequencies and low frequencies, and they're always separated so that I kind of get good estimates. That's what happened in here. High frequencies and low frequencies were separated, and so I got good estimates. Here, they're not even separated, so I'm really just, I'm really in trouble.
The previous packet idea was just more separation, which was not creating the continuous, like frequencies and errors. Or
What do you mean, this?
No, I mean, this is now what's happening, and I can see this. But there was this idea about
Yeah. What's changed is that we have to obey the Goldilocks rule.
Precisely.
You have to obey it exactly. It's like once you've made a choice of what the intermittency correction is that appears on the right-hand side of the inequality, you're just stuck with it. That's what this schematic is depicting. You're just obeying the same rule over and over again and creating these velocity increments with near enough frequencies. And so the only solution to this, the only possible solution is that WQ plus 1 has to have disjoint spatial support or space-time support from all velocities with frequencies in between lambda Q and lambda Q. And now we've arrived at this concept of a wavelet scheme because we've lost some of the frequency separation. And the only way to compensate in order to save the day here is to substitute in spatial support separation. All right. All right. So, there's no good way to do this besides to just basically completely reformulate this inductive setup. We have to reformulate it. So let me describe how we're going to reformulate it. The first thing I'm going to do is I'm going to rename some of the frequencies. So I'm going to leave lambda Q the same, but I'm sick of writing fractions in between 0 and 1. So I'm going to change lambda Q plus 1. I'm going to now start calling this lambda Q plus n bar. All right. And then I used to have all these intermediate frequencies, which were like, lambda Q to the alpha, lambda Q plus 1 to the 1 minus alpha, or alpha and 0 and 1. And these are now they're just lambda Q plus k, or 0 less than equal to k less than 0. So no more fractions. We're just lambda Q plus 1, lambda Q plus 2, all the way up to lambda Q plus n bar. And n bar is still serving kind of the same role. It's describing, in some sense, the fineness of some frequency chopping. But what's changed now? Well, the maximum frequency of UQ is now going to be lambda Q plus n bar minus 1. And the frequencies of WQ plus 1 equals UQ plus 1 minus 3Q. This is going to be lambda Q plus n bar over 2, lambda Q plus n bar. This is the analog of lambda Q to the 1/2, lambda Q plus 1 to the 1/2, lambda Q plus 1 in the old labeling system. And we're also going to rename the Goldilocks parameter. It used to be lambda Q over lambda Q plus 1 to the 1/2. And now it's going to be lambda Q over lambda Q plus n bar to the 1/2, which, if you write it out, is basically, morally speaking, the same thing as lambda Q plus n bar over 2, lambda Q plus n bar 2. All right. This is the first thing we're going to do to change this inductive state. All right.
You're forgetting about inner steps in previous papers. And
No more, yeah. So, Jan is referring to the way that we tried to deal with this in the previous paper, which was not as nice as the solution that I'm presenting here, which probably means that it was pretty bad because this is already a little involved. All right. What's the next thing we're going to do to our inductive setup? We have to account for the fact that there's errors everywhere in frequency. And by everywhere, I mean that when I look at RQ, it's not just going to have frequencies up to lambda q. It's going to have frequencies up to lambda q plus n bar minus 1. So 1 tick mark before the velocity field that I'm about to add. And so we're going to split up those errors into different shells, where the superscript refers to the frequency in between lambda q plus 1 or lambda q plus n bar and lambda q. So lambda k is in between lambda q and lambda q. So this RQK is a frequency lambda. And we're going to have to do the same thing with the phi's. Phi, okay. All right. And the next thing we're going to do is well, how should we say this? Yeah, so we're going to still use the notation WQ plus 1. And we're going to split it into the 5 parts and the R parts. But it's not going to get rid of all of these errors. It will only correct RQQ and phi QQ, i.e., it's only going to correct the lowest frequency of the errors that I have at step Q. And this will have frequencies, like we said over here, in between lambda q plus n bar over 2 and lambda q plus n bar. And hopefully, this will create new errors, which I have to give some new name to. So S Q plus 1K. At frequencies lambda K. Or Q plus 1 less than equal to K less than equal to Q plus n bar. And in order to proceed to the next step, I have to define RQ plus 1K. And what I define it to be is the error that was already in that bin from the previous step, plus the error that I just created by adding a new velocity. All right, so this is a mess. So let's draw a schematic so that we can try and understand what's happening. What? So we still have frequencies for velocity and frequencies for errors. So let's get the colors again. Velocities, errors, and well, I have errors and frequencies. Up to, but not including lambda q plus 9. And I have velocities at frequencies up to, but not including lambda q plus 9. If I want to draw this. I'll stop right before I get to it. And so these errors, these are the RQ tags and the pi q tags. And these velocities are WQ, WQ minus 1, etc. And I'm now going to add WQ plus 1, which has maximum frequency lambda q plus n bar. And WQ plus 1 is hopefully going to create a host of new error terms which live here. Let's not draw them, we have the old ones. The old ones aren't going away. Understand? Let's draw them just above. And at the last bin, there was nothing already in the last bin. The last bin is only populated by an error term which I made by adding WQ. All right, so I take a collection of errors, live between lambda q and lambda q plus n bar minus 1. I leave most of them alone, and I just want to get rid of the bottom one. And I get rid of the bottom one by adding WQ plus 1. And that's going to make a whole host of new errors, which have shifted to the right by 1. And the last ingredient that we're going to put in our inductive steam is the following assumption. So the support in TNX of WQ intersect the support in TNX of WQ prime. This is empty if Q minus Q prime is less than M bar.
Equals
Right.
empty set.
Say again?
I said equals empty set.
Ah, yes, equals 27. Thank you, Dallas. This is half of my assumption on how to separate these different velocity increments. The other half is an assumption on the frequency of their Fourier, the frequencies of their Fourier. And this is going to be the empty set if Q minus Q prime greater than.
Equals to empty set or it doesn't equal it?
Oh, goodness. All right, that should be right. Okay. Um, all right. So, I have 10 minutes, a little less than 10 minutes left. And what I want to do in those 10 minutes is give you some indication of how we ensure this separation with spatial support. All right. So, all right. So in order to ensure the spatial support separation, I have to tell you something about what this actually is. All I've told you so far is information about the frequencies of that thing. So what we're going to do, I'm going to use the letter which is consistent with the letter that we used in the paper, because otherwise we'll get confused. So we'll replace these W2 plus ones with something that I call, or that we call B, and the B stands for bundle. All right, so what is this B? It's an intermittent type bundle, and I'm going to use some pictures of what it looks like. So let's do the one for the Reynolds stress, because the picture doesn't care about whether it's Reynolds or right there. So let's do one in the E3 direction, because you can just rotate it and get something else in the other directions. So it's going to be a product of two functions which depend on not x3, but x1 and x2. And what are these W lows and W highs? So let's give these colors. It's purple. Let's say. So these are functions of x1 and x2. I'm going to draw the torus in the x1 and x2 variables and show you where these things are supported. So let's make tick marks as spacing lambda q plus 1 inverse away from each other. This is the new lambda q plus 1, not the old one. And inside of each of these little cells, W low is going to consist of some little circle, which I am allowed to move around inside the box. All right, so this consists of supported in balls of radius, lambda q plus 1 inverse, and also spacing lambda q plus 1 inverse. So this object has these little balls, which are spaced at a distance which is commensurate with their diameter. And so this thing is basically supported at exactly frequency lambda q plus 1. There's not much smearing out of frequencies here because the spacing and the thickness are the same. So the minimum frequency and the maximum frequency are basically the same. But what happens when we zoom in on one of these little balls? Now we see the support of W pi, which looks like a bunch of very fine little balls. And what are the dimensions of these things? So the dimension of one of these balls is lambda q plus n bar inverse. And the spacing between neighboring balls is lambda q plus n bar over 2. So this is coordinate balls, diameter, lambda q plus n bar inverse, spacing lambda q plus n bar over 2 inverse, which means that this frequency support is lambda q plus n bar over 2 lambda q plus n bar. And why have I shifted all these little objects around? It's because the shift helps me ensure that these little bundles are dodging the old bundles. So we choose the shifts. To ensure that WQ plus 1 is this one, WQ, WQ minus 1, all the way down to WQ minus n bar. And in the last 1 minute, what I'll say is that in real fluids, turbulent little eddies don't just stay where they are. They move around. So turbulent high frequency eddies are affected by the lower frequency velocity. By velocities of lower frequencies. Which means that this whole picture with a nice stationary object at a fixed time slice inhabiting the torus, it actually has to be translated into something which lives in Lagrangian coordinates adapted to the low frequency velocity field. So we have to put the bundles in Lagrangian coordinates adapted to U. And this is pretty technical undertaking. And instead of getting into it with -1 minute left, I'm just going to stop. And if you want to ask me something about this, I'm happy to chat some more about it. But let's just stop here. Thanks for your time.